Okay. Hi, everyone. I'm Greg Good. I'm the director of the Center for History of Physics here at the American Institute of Physics, and welcome to the second Trimble Lecture of 2018. I want to thank you all for coming and be sure that we acknowledge especially the people who are here who have helped to support the programs in history at AIP, the donors. Many of you have donated to the Physics Heritage and Promise, and we're very thankful for the help that you've given us. It's pushing us towards a number of the goals that we have, supporting both the Library and Archives and the Oral History Program and the other programs that we run here in the building. So this is our second talk of the year. We are introducing some innovations as we go along. At the first talk, for the first time, we had a professional crew helping us with the video, and today we're adding to that live streaming on YouTube. The people who are on YouTube, I'm sure there are 2 or 3 of you out there, we don't know. We will find out when the stats are run. But if anyone who's watching on live stream wishes to ask a question of the speaker during the Q&A at the end of the talk, we will accept your questions by emailing them to me. And my email address is ggood@aip.org. So keep that in mind if you're watching on live stream. And give us an idea, too, if you have some feedback on the quality or the performance of speakers like me. Maybe I need to speak more clearly for you. I don't know. Tell me whatever reactions you have to the live stream. Thanks. So in addition to me welcoming you here, I would like also to ask our new CEO, Michael Maloney, to just say a few words. Michael has been with us now for about 5 months, 6 months, 6 months now. Okay, an anniversary. So, Michael.
Great, thanks, Greg. And tonight's really not about me, so I'm going to keep this really short. And also, Greg didn't give me a heads up, so that's okay. But just want to welcome you to AIP and the American Center for Physics. I'm sure many of you have been here before. I joined, as Greg mentioned, AIP back in March. It's a really exciting time to be here. We're involved with a lot of different initiatives, new activities. I'm assuming because you're here, you're interested in the history programs and the Niels Bohr Library and Archives, which is actually going through tremendous expansion and change. And it's a really exciting time. You probably know about the arrival of the Wenner collection here, which really broadens and deepens our collection of rare books in a way that's really a step change. Is not a quantum leap. It's really not even adequate to explain the change that's happening in the archives and the library that we have here. So it's very exciting. I hope many of you will have an opportunity to hear more about that in the weeks and months ahead. But let's get back to business, and very welcome here again.
Okay, thank you, Michael. So before I introduce the speaker, I want to call a heads up on the 2 more Trimble lectures that are coming up this fall. On October 3rd, which is not that far from now, Jimena Canales will be here to speak about the trouble with Einstein's time. Some of you may be familiar with the book that she published on Einstein and the concept of time. Then on November 14th, Benjamin Wilson will be here speaking on strategies of stability, knowledge, secrecy, and the Cold War nuclear arms competition. So a very diverse program over the next few months. And then in 2019, we'll have another 4, which are still being finalized. So I'll try to get those talks finalized in the next few weeks so that I can announce them at the next one. So for tonight, our speaker is Mary Jo Nye. She is Emerita Horning Professor of the Humanities and Professor of History at Oregon State University in Corvallis. And in 2017, she received the Abraham Pies Prize for the History of Physics awarded by the American Physical Society and AIP. And we're very glad to have Mary Jo here to speak about her experiences in the writing of the history of physics and how that has changed over the last few decades. So, Mary Jo.
I think this is on. Can you hear me? Yeah. Good. Thank you so much, Greg. It's a great pleasure to be here, and it's daunting in a certain way to have arrived in the face of the oncoming hurricane. But we're all hoping for the best for everyone. Can this be turned up a little bit louder? Yes. I don't think I'm in control of it. And also a little bit daunting to learn that this is being live streamed, but that's fine. It's an experiment, and we'll see how it turns out. I was very much honored to be invited to give the Trimble lecture during this current series of the Trimble lectures endowed by Virginia Trimble in honor of her father. And I appreciate very much the invitation to come here and the hospitality that I have enjoyed, and my husband, who's also with me, another historian, to observe me historically. And I've enjoyed, very grateful to Gregory Good for the hospitality that he's given us, and also to Stephanie Jankowski for all of the preparation that she has done for my visit. Beginning now, let me say, getting this all together, about this time every autumn, for many, many decades now, we await announcement of the year's Nobel Prizes. This year, the Physics Prize announcement is scheduled for Tuesday, October 2nd, no earlier than 11:45 a.m. Physicists, chemists, science journalists, research administrators, and historians of physics wonder about the outcome. But what does the prize tell us? Among other things, it tells us what some elite physicists consider to be the most important achievement, or two achievements, of the last few years or the last few decades, and what combination of 1 to 3 people should receive credit for the work. We may ask, however, whether the prizes, over time, convey the full range of research fields in physics or the numbers of researchers in each field. Do the awards respect disciplinary boundaries or challenge them? How do factors other than the quality and significance of the work influence the Nobel decision? And how meaningful is the status as winner that comes to individuals, theories, institutions, and nation states through the Nobel Prize awards? These are questions that we might also very well ask about the history of physics. In an important sense, historians of science do much the same kind of work as the Nobel process. And historians often observe something similar to the Nobel 50-year cutoff rule that conceals the inner workings of nominations and Nobel Physics Committee deliberations from public view. There often is a notable lag time between the date that scientific work is first done and the time of either a Nobel Award or a historical narrative and interpretation. For many younger historians, if it occurred in her lifetime, it's not history. In my talk this evening, I have the Nobel Prizes in mind as I consider the question of how accurately histories of modern physics capture the various and shifting domains of physics, the changes in theories and practices, and the relative credit given different theorists and experimentalists. Furthermore, I examine how histories of physics have been changing over the last few decades. My focus is principally on the physics of the 20th century, which coincides with the Nobel Awards, and on histories of physics written since the 1960s, when the history of science became an expanding science discipline, an expanding academic discipline rather, practiced both by physicists writing history and by professional historians. I will begin by discussing two aspects of 20th century physics that often are remarked upon: its fragmentation into specialties and its corresponding increase in collaborative authorship and teamwork. I then will turn to some trends in the ways in which the Nobel Prizes, decided by physicists, have made awards for different fields of physics and for sets of theories and experiments to individual physicists. I conclude with a longer discussion of how histories of physics, like the Nobel Prizes themselves, have sometimes distorted the history of physics as a whole, particularly who counts and what counts, but also how historians of physics have adapted to changes in physics and adopted historical approaches that vastly enrich the history of physics beyond a Nobel tale of heroic winners and losers. In a recent article in Physics Today, the historian of physics, David Kaiser, reminds us of a keynote lecture that Carl Darrow, the atomic physicist and American Physical Society executive secretary from 1941 to 1967, gave at an American Institute of Physics meeting in Chicago in October 1951. Asked to speak on the whole of physics, Darrow said that he found the task impossible, and that the last man who might have done this had been Hermann von Helmholtz at the end of the 19th century. As Kaiser writes, 20th century fragmentation and specialization in physics is reflected by entries from the 1940s to the 1970s in physics abstracts. The number of published abstracts increased from about 4,000 just after the Second World War to 7,500 in 1948, and then to 84,000 in 1971, doubling every 6 years from 1945 to 1971. It was also around 1970 that the number of physics PhDs in the USA, as many of you know, hit their peak before a decline that briefly almost totally reversed for a while in the early 1990s. Corresponding to the doubling every 6 years from 1945 to 71 of abstracts published in physics abstracts, the number of subject areas within physics increased. In 1930, there had been 8 main categories listed here, as you can see. In 1955, nuclear physics appeared as a category, divided into 6 subfields. And by 1965, nuclear physics had 35 subcategories. Solid-state physics, which became a named division within the APS in 1947, had 38 subfields in 1965. Physics journals changed, of course, in response to these developments. Beginning in 1963, Physical Review was printed in 2 sections, one for solid-state and atomic physics, and the second for nuclear and high-energy physics. By 1967, the journal was divided into 5 parts, a pattern of subspecialization followed by other physics journals, such as Physics Letters and Zeitschrift für Physik. By adding the study of the properties of liquids to solids in the 1960s, the category condensed matter became an umbrella category that included the solid state and was used in journals, physics societies, and research groups. Approximately 1/3 of American physicists came to identify themselves as condensed matter physicists by the late 1990s, with problem domains and methods that often overlap with materials science and more recently with nanoscience, of materials that range from a few atoms to 100 times larger in scale and in size. Like their colleagues in nuclear and high-energy physics, condensed matter physicists frequently make use of fundamental quantum mechanics, but unlike their quantum physics colleagues who focus on elementary particles and fields, condensed matter physicists concern themselves with many atom systems, mainly in the solid and liquid states. Associated with the increased specialization in physics was the growth of collaborative research, a trend that also accelerated after the Second World War. Physics had seemed a heroic science during its first centuries, epitomized by giant figures such as Newton or Helmholtz or Einstein, who could do it all and who knew everything while making revolutionary discoveries within their scientific communities. The heroic figure still was front and center just after the war, when Robert Oppenheimer, the theoretical physicist and director of the Manhattan Project, became an iconic figure who could be identified publicly simply by a photograph of his pork pie hat. In contrast, decades later in 2012, when two experimental teams at CERN's Large Hadron Collider simultaneously announced the experimental confirmation of the Higgs boson, formal recognition and authorship was collective. The teams, each composed of thousands of members affiliated with hundreds of different institutions, simultaneously announced their observation of the Higgs particle in the same issue of Physics Letters B, one team under the authorship of the Atlas collaboration, led by Fabiola Giannotti, and the other under the name of the CMS collaboration, led at that time by Guido Tonelli. Not all research teams are so large, of course, but single-authored research became increasingly uncommon during the course of the 20th century. A few years before announcement of the Higgs boson, historian of science Mott Green noted in an article on Scientific Biography that the modal number of authors on a research paper in Nature and in Science in the early 2000s was 8 co-authors. As a historian, Green worried that the rationale for the biographical organization of the history of science was coming to an end, a worry that in fact was not new. It surfaced around 1960, when sociologist Derek Price noticed that 80% of papers in chemical science were multi-authored, in contrast to only 20% around 1900. Price reported that the average number of co-authors in chemistry had increased from 2.7 in 1946 to 9.5 in 1963. He dramatically and wrongly predicted, if the trend holds by 1980, we shall move steadily towards an infinity of authors per paper. Price used the term big science to characterize what was happening, as did Alvin Weinberg, the director of Oak Ridge National Laboratory, in what became a famous article by Weinberg published in Science in 1961. As noted by historian of physics Peter Gallison, the Brookhaven Laboratory particle physicist Alan Thorndike captured the strongly collaborative character of modern scientific research in 1967, saying, "The experimenter is not one person, but a composite. He might be 3, more likely 5 or 8, possibly more. He may be spread around geographically," note the he, although more often than not, all of him will be at 1 or 2 institutions. He may be ephemeral with a shifting and open-ended membership. He is a social phenomenon. One thing, however, he certainly is not. He is not the traditional image of a cloistered scientist working in isolation at his laboratory bench. Modern collaborative research has many advantages. Some things can only be discovered collaboratively, and there is evidence that collaborative work generally assures higher quality of results and wider recognition. For example, in prizes and awards. The expanding scale of collaboration in the 20th century reflects many factors, foremost among them increasing specialization within research groups or teams in which new kinds of instruments and computers require expertise or computing skills that the laboratory director or project manager might not personally possess. One of the examples that I have studied is the Oxford University X-ray crystallographer Dorothy Crowfoot Hodgkin, whose structural determinations for penicillin, vitamin B12, and insulin from the 1940s through 1960s included collaborators at Imperial Chemical Industries, Princeton University, and UCLA, in addition to her Oxford research group. Here you see Hodgkin with 4 of the 10 co-authors on the insulin announcement that is usually attributed to her. She, by the way, in co-authoring this, put her name 3rd from last, neither first nor last. Collaborative research also flourished after the 1940s because multiply resourced funds from government, industry, and the military, as you know, became available on a scale unimaginable before the Cold War, at the same time that travel and communication became increasingly easier, not only physically, but digitally. Let me turn now to the Nobel Prizes and examine the extent that they mirror shifts in specializations and collaborations over time. A quick way to identify leading fields of research and breakthrough achievements in physics has long been the Nobel Prize. It is perhaps the foremost of international awards, and certainly the one that garners the most public attention, for good or ill. The prize has been awarded since 1901 by the Swedish Academy of Sciences on recommendation from the Academy's Nobel Physics Committee, which is formally composed of 5 voting elected Academy members and a secretary, also a member of the Academy. Each committee solicits nominations made by themselves and other Academy members, former Nobel Prize recipients, and eminent professors in physics in Nordic countries and elsewhere. The originally Western geographical base for the prize gradually expanded, with the Physics Committee first soliciting nominations from Japanese physicists in 1910, for example, and from Indian scientists in 1929. The original intent of the prize was to recognize the most recent important discovery or invention in the domain of sciences, in the domain of physics, although the notion of recent became incredibly flexible in the hands of the Academy. From its beginning, the Physics Prize helped establish the notion of progress, even revolution, in physics, with early awards given for relatively recent experiments and theories in the early 1900s on radiations, radioactivity, atoms, and electrons. Negotiations between the Nobel Physics Committee and the chemistry committees account for some of the decisions about whether a prize, for example in radioactivity, would be given in chemistry or physics. But as historian of physics Helga Kroh notes, the relationship between physics and chemistry was not symmetrical. Thus, over time, a large number of chemistry prizes were awarded to scientists whose work usually is considered physics, but not the other way around. From the 1930s on, the Physics Prize most often recognized in the next few decades work in radiation and spectroscopy, quantum mechanics and electrodynamics, and elementary particles, such as the electron, proton, neutron, mesons, lepton, etc. Initially, astronomy and astrophysics were unofficially excluded from the Physics Prize, a trend reversed in 1967 by the award to Hans Bethe for his 1938 theory of stellar energy production, which had to do with nuclear physics. Astrophysics and astronomy received 5 awards from 1974 to 2011, including the 1983 award to Subramanian Chandrasekhar and William Fowler for investigations of the formation of chemical elements in the universe. Arguably, the first Nobel Prize in condensed matter physics was the 1913 prize to Heikki Kammerlund-Onnes for low temperature studies in the production of liquid helium, with Lev Landau explicitly recognized in 1962 for what were called his theories on condensed matter and especially liquid helium. Prizes for research on superfluids, superconductors, crystals, and metals followed. Since Nobel Prize winners subsequently become Nobel Prize nominators, an expanding number of condensed matter Nobelists presaged increased numbers of awards in this field. The sociologists Eve Gingras and Matthew Wallace have analyzed trends in the physics awards for the years 1901 to 2000, using an 8-category scheme adapted from the classification that was developed by the American Institute of Physics. In a more recent analysis, Hamish Johnston, an editor at physicsworld.com, published by the Institute of Physics in London, used 7 categories to classify prizes. And I'm not going to spend a lot of time with this, but it's a very interesting infographic. Both Gingras and Wallace and Johnston find that nuclear and particle physics account for at least 1/3 of the Nobel Physics Prizes by subdiscipline, dominating the awards in the 1950s and 1960s. In Johnston's scheme, nuclear and particle physics, in combination with quantum physics and atomic, molecular, and optical physics, account for 57% of prizes and laureates since the beginning of the Nobel Prizes. Although more than 1/3 of American physicists now identify themselves as condensed matter physicists, their share of Nobel Prizes has been proportionally smaller, which shows that the percentage of awards and laureates in this infographic shows that the percentage at about 22%. Now, obviously, you can count fields different ways. and the Nobel Prize official website has a different way of counting fields, and they divide physics into 40 fields, and they list some laureates in, of course, more than one field. But I use this one just by way of generalization. Thus, in various arrangements of physics fields, the Nobel Awards appear historically to have favored other fields over condensed matter physics, but this clearly has been changing. It should be noted, too, that chemistry awards have recognized the condensed matter field with at least 4 awards, including the 1998 prize to physicist Walter Kohn for his work on the electronic properties of metals and his development of density functional theory. The infographic in figure 4, which bears looking at if you could see it better, indicates how shared prizes became more prevalent about 1950, with the last 2 unshared prizes in 1991 to Pierre-Gilles Dejean and in 1992 to Georges Charpak. As I alluded to in my opening remarks, a Nobel rule limits an award to no more than 2 achievements and 3 living scientists. Although the 1903 prize was divided among 3 scientists, Pierre and Marie Curie and Henri Becquerel, a 3-person award did not occur again until 1956 for William Shockley, John Bardeen, and Walter Brattain, recognizing their investigations at Bell Labs on semiconductors and discovery of the transistor effect. Most physics awards before the 1950s went to a single person, reflecting the pre-1950s trends in publication, authorship, and attribution of leadership that I discussed earlier. Only 2 women have received the Nobel Physics Prize, in both cases as a shared prize, Marie Curie in 1903 and Maria Geppert-Mayer in 1963, each of them married to a male physicist at the time. As Helga Krah notes, since they each received a quarter of a prize, the grand total of women's Nobel Physics Prizes is 1/2. A situation hardly remedied by the recent award to astrophysicist Jocelyn Bell Burnell of a special breakthrough prize in fundamental physics. The role in recent physics of very large, internally specialized research teams has begun to bring into question the award of each Nobel Prize to no more than 3 individuals. Most recently, in the cases of the 2013 prize to theorists Francois Englert and Peter Higgs for the Higgs boson, and the 2017 prize to Rainer Weiss, Barry Barish, and Kip Thorne of the LIGO-Virgo collaboration for observation of gravitational waves, all of whom have made public statements very conscious of the collaborative effort that went into this, for which they received recognition by the Nobelists. It seems unlikely, however, that scientists or the public will easily relinquish the notion of the standard bearer, the gifted leader, but it's not impossible that the Swedish Academy could change the rules and award the prize to a group, as has been the case since 1904 with the Peace Prize, awarded by a committee chosen by the Norwegian Parliament. Indeed, there was an attempt at collective authorship and responsibility at the very beginning of scientific institutions when the Paris Academy of Sciences was founded in 1666. The intention was to submerge individual egos to the general good and to give credit for individual members' contributions to the Academy as a whole, as Francis Bacon originally had prescribed in the 1620s for what he called the new science. The Paris Academy, however, abandoned that formula in 1699 and began assigning credit to individual scientific contributors, as has always been true of the Royal Society in London since its establishment in 1660, and of course has remained scientific tradition. I turn now to historians of physics and to what we may see as both stability and change in the history of physics as it has been written since the 1960s. I agree with historian of physics Richard Staley that a focus on scientific revolutions and on physical theories has remained very strong over decades in the history of science for a number of reasons. But There also, as Staley also says, there has been increased attention since the 1960s to social and political context of science, the experimental and material dimensions of science, including the practices of research groups, and the institutions of big science. There is less heroic history, and there are more heroines in recent histories, but the notions of intellectual genius and charismatic leader nonetheless remain commanding tropes in histories of physics. In the 1960s, when the history of science and science studies was becoming a professional academic field, when I myself was first beginning to study the history of science, the mainstream topics in histories of physics and in histories of science more generally were a repertoire of 17th to early 20th century physical science, classical atomic and molecular theory, quantum theory and relativity, along with the Copernican and Newtonian revolutions, as well as 18th and 19th century theories of electricity, heat, and light, and the chemical revolution. Thomas Kuhn's wildly popular book of 1962, Structure of Scientific Revolutions, focused on this very range of subjects and made them examples of scientific paradigms and paradigm change at the heart of engagement within the history and philosophy of science. These subjects remain a substantial part of histories of physical science today. Kuhn shifted many historians' interest away from a heroic history of ideas and individuals towards histories of groups and communities. In other words, from histories of eureka moments of discovery to histories of communication, organization, and social context. The move towards social history and sociology of science was not Kuhn's doing alone, however. For one thing, the trend in the general historical profession of the 1960s led away from intellectual history and towards social history. But importantly for science historians, some influential scientists, such as Oak Ridge National Laboratory Director Alvin Weinberg, shown here with Senator Kennedy, and the father of the current Al Gore, he was one of those scientists who began speaking out about the organization of science and how it had changed in the era of what he too Weinberg called big science. Among scientists who addressed these matters were some whom I have written about myself, such as the nuclear and cosmic ray physicist Patrick Blackett, the X-ray crystallographer J.D. Bernal, and the physical chemist and chemical physicist Michael Polanyi. Another scientist who very directly affected the way in which historians and sociologists thought about science was the condensed matter physicist John Zeeman, who set out self-consciously to reorient historians and philosophers of science toward social studies of science, and toward Zeeman's own epistemological view that science is reliable and verifiable knowledge reached by consensus rather than transcendent truth revealed to genius. With this perspective, some science historians began to ask how reliable science is constructed rather than how scientific truths are discovered. And many science historians turned toward the study of scientific communities and institutions. Take, for example, the journal Historical Studies in the Physical Science, now transformed into Historical Studies in the Natural Sciences. The journal was first established in 1969 under the editorship of historian Russell McCormick, then at Johns Hopkins University. The journal's emphasis was mainly 19th and 20th century physical science. Published articles were notable for their frequent focus on social history alongside theoretical and experimental history. From 1980 until 2008, under the editorship of Kuhn's former student, John Halbrin, the journal also opened its pages to histories of the increasing variety of subfields of physics, with about 70% of its articles devoted to the 20th century. Stellar energy, astrophysics, cosmic rays, and geophysics joined quantum physics and atomic theory in the journal, in the form of histories of theory and experiment, but also in accounts of arrays of institutions and research groups that included Bell Labs, Brookhaven Laboratory, the Geophysical Laboratory, CERN, the Lawrence Berkeley Laboratory, the AEC, the NRC, and military research. Among new specializations in physics, solid-state physics debuted in Historical Physics, Studies in the Physical Sciences in 1981. in historian Lillian Hodison's article on the point contact transistor, followed by other historians' articles on imperfect crystals, superconductivity, and the electron theory of metals. In other words, historical studies in the physical sciences was capturing faithfully the mainstreams of modern physics as they had been developing since the Second World War, including the fields of solid state and condensed matter physics practiced like particle physics in increasingly complex networks of institutions and collaborations in university, industrial, military, and governmental settings. Do these examples from one leading journal, one of the most important journals in my field, suggest that historians generally were writing about different fields of physics, especially condensed matter physics, in proportion to fields, practice, and strength among physics? It appears that this is not the case. In Physics in Perspective, Studies in History and Philosophy of Science, Studies in History and Philosophy of Modern Physics, there's also a modern science journal, and the European Physical Journal H for Historical Perspectives on Contemporary Physics, as well as in books and essays directed at both professional and popular audiences. It is particle physics, quantum physics, relativity, and their founding pioneer heroes that by and large have remained favored genres in history of physics. As Richard Staley also wrote in 2013, we know much less about the work of the vast bulk of the physics discipline than we do about major theoretical developments and high-profile elites in particle physics. Why is this the case? Let me suggest three related reasons. First, I think we can safely speculate that narratives of revolutionary science make considerably more gripping stories than the industrial-linked and often non-converging fields of solid-state and condensed matter physics. Michael Eckert, a historian of solid-state science, notes that the popular, if controversial, Kuhnian model of scientific revolution and scientific growth does not work for solid-state physics. That's what Eckert says. There were no switches of incommensurable paradigms, he suggests, or there were too many of them on a small scale. Noting that experimental achievement has been more central than theoretical work to the Nobel Award since the 1980s, the sociologist Gingras and Wallace suggests that the strong recent recognition of experimental work reflects the absence of major paradigm shifts in physics since the late 1960s. Helga Krah writes that what most people would single out as the most profound and wide-ranging conceptual innovations of the 20th century are relativity and quantum mechanics, and that solid-state and condensed matter physics are examples of the kind of progress that results from extending knowledge already opened up for research by more precise measurement or by developing new instruments. Secondly, the large segment of physics that falls outside the fields of elementary particle physics, gravitational physics, and astrophysics appears to register lower down the rungs of a persistent hierarchical ladder defining intellectual status. Egon Orawan, one of Michael Polanyi's colleagues, lamented in the 1960s, for example, that his and Polanyi's earlier researches on the strength of materials, the kind of research that Wolfgang Pauli famously called dirt physics, had been, Erawan says, it was a prosaic and even humiliating proposition in the age of de Broglie, Heisenberg, and Schrödinger. Similarly, historian of physics Joe Martin, whose new book on the history of solid-state physics will appear this year, finds that the broad range of publicity and newspaper coverage for Nobel Prize awards associates high-energy physics with fundamental intellectual insights into the universe, its origin and meaning, in contrast to descriptions of solid-state and condensed matter research as useful and applied science connected to chemistry, metallurgy, and engineering. Martin calls this phenomenon prestige asymmetry. Thirdly, in relation to prestige asymmetry, let us note that the greatest prestige, no matter how much we know about a research achievement's organization, instrumentation, economic funding, political background, and other factors, the greatest prestige still goes to the one or few individuals who are in charge, who have responsibility, and who seem rightly to deserve credit. The history of physics still needs to find heroes and heroines, and many of the easiest of them to identify are the founders of quantum theory and relativity theory. Albert Einstein still by far dominates histories of modern physics, and will continue to do so as more and more of his papers and correspondence appear in the collected papers of Albert Einstein, now in its 15th of 30 projected volumes published in print and online. And some of you may have heard Diana Barkin's lecture here last year in the Trimble series that has to do about her work with the Einstein project. Prominent too remain Isaac Newton, Galileo, and the late Stephen Hawking, whose burial service at Westminster Abbey last March was attended by more than 1,000 people. Marie Curie, Robert Oppenheimer, Richard Feynman, and Werner Heisenberg are among the other iconic figures in the history of physics and scientific biography. In the last decades, many historians often have refocused their studies from a single individual to small groups, such as scientific families, or scientific couples, or scientists working together as a laboratory research group, or scientists in the same research field. Laura Otis has written what she calls a labography that examines professional and personal relationships between a scientist father figure, in this case the distinguished 19th century German physiologist Johann Müller, and 7 of Müller's protégés and students, with detailed descriptions of where they lived and worked, how they competed with each other, and how the former students gradually struggled to win their own reputations and independence from their Dr. Vater. This might well be a model for some histories of 20th century science. Writing histories or biographies of large-scale collaborative projects and groups is not easy. Wolf Beigelbach, editor of the European physical journal H, which has to do with the history of contemporary physics, has called upon historians to collaborate with physicists in order to better write about the physics of the last 50 years. This is an approach already adopted by some historians, like Lillian Hoddeson, for example, whom I earlier mentioned. Her 1980s articles in Historical Studies in the Physical Sciences presaged her later collaborative books, Crystal Fire, The Invention of the Transistor and the Birth of the Information Age, written with Michael Reardon, Fermilab, written with Adrian Kolb and Catherine Westphal, and Tunnel Visions, The Rise and Fall of the Superconducting Supercollider, written again with Michael Reardon. On the other hand, Hoddeson, like many historians, has not abandoned the idea of genius. Her biography of John Bardeen, written with Vicky Datch, is titled True Genius. In winding up, let me say that histories of physics have changed in many ways since the 1960s that mirror changes in physics itself over the course of the last half-century, including the reflection of physicists' own choices for attribution to the Nobel Prize. In general, as I have discussed, many historians have favored attention to some fields of physics, particle physics, high-energy physics, astrophysics, and relativity, over other areas such as solid-state and condensed matter physics. But this has definitely been changing. Historians Robert Crease and Catherine Westphal have called attention recently in an article in Physics Today to what they call the new big science that has emerged in the last decades as U.S. national laboratories have constructed accelerator-based radiation and neutron source machines for studying structural and behavioral properties of matter, including biological molecules, at the electronic, atomic, and molecular levels, while shifting an increasing proportion of high energy and nuclear physics research to facilities abroad, particularly to CERN. Historians of science and historians of technology increasingly have been paying attention to condensed matter, materials, and nanosciences and technologies, reflecting the trends in recent physics. And there's been quite a bit of work in recent years by historians of physics, and historians of science in general, on materials science and nanoscience. The current membership of the 2018 Nobel Physics Committee includes representatives of the fields of nanoscience and biological physics among the scientists on that committee, as you can see here in this list of Academy members and their fields. Still, in 2018, the Nobel Prize likely will bring attention to only a few physicists, perpetuating the culture of scientific heroes, unless they have surreptitiously changed the rules. In contrast, as I have discussed, historians of physics and popular science writers, while often focusing on heroes and heroines, also have been writing histories of institutions, laboratories, and research groups, including histories of collaborations, large collaborations, in research settings that are very, very different from classical or even early 20th century physics. We should note, too, that historians of physics often put women scientists who have been abandoned by Nobel recognition back into the picture of physics as a whole, one of the important trends in histories of physics in the last decades. Finally, let me conclude with some observations about reductionism, paradigms, and scientific revolutions in histories of physics. Philip Anderson has argued since the 1970s that complexity involving the conception of emergence is what he calls the fundamental philosophical insight of late 20th century science. Physicists investigating many-body problems, many-body systems, have been discovering behaviors that cannot be predicted or understood on the basis only of the fundamental laws of elementary particles and wave mechanics, he writes. Going on to say, properties emerge from solutions of equations that are not readily apparent from the equations themselves, so that condensed matter physics is not just applied elementary particle physics. In a review this summer in Physics Today, physicist Michael Stone calls emergent behavior the central paradigm of condensed matter physics. Among historians of physics, Sam Schwaber, himself a theoretical particle physicist, was one of the first historians of physics, I think, to remark on the concern of many particle physicists that the reductionist approach that, as Sam put it, has been the hallmark of theoretical physics in the 20th century is being superseded, he wrote, by the investigation of emergent phenomena. And that, physics, it could be said, is becoming like chemistry. Schwaber, as a theoretical particle physicist, worried about the future of his field and its quest for reductionism and unified understanding of the physical world, since in his view, high-energy physics and condensed matter physics were becoming decoupled despite ongoing interchange of ideas. As historians more and more engage with developments in late 20th century physics, it may be useful to consider the question of whether one of Kuhn's paradigm shifts has occurred, emergence, or rather whether two different but not incommensurable ways of seeing the world have come to characterize physics. If so, if two different but not incommensurable ways have come to characterize physics, then physics may be arriving at an epistemology not so different than the epistemology of chemical and biological science, in which the notion of emergent properties has long coexisted with the search for basic elementary bodies and fundamental laws. For historians, among whom I include myself, there is a continuing challenge to describe and interpret the processes of specialization, collaboration, and problem choice that have characterized modern physics and led physicists increasingly to cross disciplinary boundaries into both the chemical and biological sciences, where it is sometimes necessary to relinquish the reductionist paradigm. Thank you for your attention.
Okay, thank you very much, Mary Jo. So if we have questions, I'll pass the microphone to the people who have questions, so have a little patience while I get to you. I want to say that we did have a few viewers on live stream, 2, and plus me, and it was working great. So thank you very much to the technical team that's here. And we have some comments. Michael Burani is in Australia, I think. Last I was aware of where he was, that's where it was. And he has a few comments that I'll share with Mary Jo later. They might be of interest to her. That I can't read them with the glasses that I have on right now, so I'm going to leave them be. And Ingrid Aukert is up in Philadelphia watching this on her living room TV set. So, hello, Ingrid. Hello, Michael. So, first question.
Hi, Mary Jo. I'm Lindley Darden. We knew each other back
Yes.
when. It's nice
Hi
to
there.
see you
Nice
again.
to see you.
And I'm a historian of biology in this setting. And I have written about interfield theories and looked at interdisciplinary interactions and the role that those play. And from your abstract, I thought perhaps you would be talking a bit about interdisciplinary activities, but you instead talked about fragmentation. And we saw our interfield theories work as an alternative to the reductionism perspective, which you talked about at the end. As a philosopher, we have difficulty defining emergence, so some of us are skeptical of using that term. But integration of combining ideas from one discipline with another and getting new insights as a result of that seems to be a very fruitful thing in certain historical episodes that I've looked at. So I just wondered if you had any comment about interdisciplinarity as opposed to the fragmentation of disciplines, which seem to be your topic.
I'm glad you asked that question because clearly it's come across as fragmentation and specialization. And one of the things that I was trying to do, and I guess I didn't do clearly, is to talk about how, say, just within physics, as new subdisciplines developed and physicists came to identify themselves by these different journals in which they publish and by different specializations and fields, that increasingly they did find themselves working on problems that crossed into chemical science and biological science. And the instrumentation, for example, that was developed, including these high energy sources for neutrons and photons and other kinds of instrumentation, is often used to study biological molecules. And one of the things that's striking to me, I mentioned Gilles de and his single Nobel Prize in '91, and that's in an area which sometimes is called, as I understand it, polymer physics. Polymers used to be the province of chemists. Chemists were concerned with long-chain molecules and with the order. De Gennes was looking at the way in which disorder becomes introduced into these long-chain molecules. And in terms of the way in which the X-ray crystallography is certainly a field that is interdisciplinary in every way because it's combining X-ray research with computer work with, in Hodgkin's case, molecules that are clearly of biological significance, huge molecules. And the study of large molecules became increasingly of interest to physicists. Neutrons used for diffraction and other kind of studies of biological molecules with the neutron spallation machines and this kind of thing. So I didn't mean to say that physics has, fragmented entirely and there's nothing interdisciplinary going on. Material science, how do people identify themselves? They're often, educated in a physics or engineering or in chemistry or some other field, and perhaps a specialization within the problems. Certain problems bring them together, and they're all working in the same labs or in different labs in order to solve something. So I'm sorry if I was unclear about that, because I didn't mean to say that everything is fragmented and no one speaks to each other and nobody's working together. I meant to say that these teams are composed of people, large teams, many of whom have individual specialties, but the team is together because of the way that they can coordinate in order to solve a problem. And that coordinator, of course, is often the work of the laboratory director or the project leader or leaders who end up having their names identified with the project and the work that's done. Although the publications very often have everybody's name on it, whether it's 8 or in the case of the CMS, 1,000 people.
Next question's here.
I was also wondering earlier in your talk whether you would get to the mixture of biology and physics, because it's rather exciting now to see that they are starting to merge a little bit. And if you think of the things that could be merged, it's very exciting. I'd like to also add that I often wondered how we got to where we were in our knowledge of science, physics particularly. And since I've been looking for about 70 years, I've seen many interesting things happen. And I wonder if the science historian is able to do enough not to look at where we got, but how we got there. And it seems like every time there is a major discovery, that's very nice, and they may get a Nobel Prize, but a major discovery very often opens up many different paths to move along based on the product of the discovery. And I've seen situations like after World War II, and the United States was doing much better in solid state than the Europeans were.
Yeah.
Why? Because we had the bucks and they didn't. So I wonder if there are enough people looking at the history of how we got where we are, more studying how we got there than what we accomplished.
I do think that many historians are interested in precisely those questions of how certain problems were chosen, why they became important. Of course, one of the things historians have often looked at, and physicists know very well, is the way in which certain problems, for example, thinking Peter Gallison's work. I mean, Peter talks about instrumentation and how, as do many other historians of physics, and how it is that various kinds of instruments then, in a sense, are breakthroughs, but then the instruments themselves become not exactly traps, but one works with the instrument and is not necessarily able to come up with any major theoretical change, working within the particular, in Kuhn's term, paradigm that the instrument has created. But I think increasingly historians have been looking at the way in which the material culture within which scientists work affects what they can do, what they choose to do. So of course through interdisciplinary contacts, because historians are interested in how new questions come up that have not been imminent in one particular discipline, but then are illuminated by another one. And certainly the intersection between physics and biology is another example of that. Say, I mean, going back to Schrodinger's turning to the question of what is life is a very famous example of how that happened. But yes, I think historians do care about how things have changed. Now, for example, you mentioned solid state physics here in the US. There are several people who have been working on the emergence of solid state physics and then of materials science in France, and how that evolved through different kinds of institutions than was the case in the United States, and why that was the case. Most of that literature is in French, but that is a question that has come up.
Before we return to the audience, I know there are more questions out there. We have a question from Ingrid Ockert. What are your suggestions for ways to teach histories of physics that emphasize groups and labs, not characteristic individuals?
Ingrid. Very good question, Ingrid. Well, one thing one can do is simply to actually talk about work that was done and concentrate, say take a particular lab or take a project and the research groups that are involved in that, and then work out a history in which what one does is to focus not just on the individual, but to focus, say, just taking one laboratory, not just to focus on the individual. Well, let me give a concrete example, which will be familiar to Ingrid because she knows a little bit about some of my work on Linus Pauling. And Ingrid I knew Ingrid at my institution, Oregon State University, and she's just finished her PhD at Princeton, and she's on a postdoc right now. But in any case, Linus Pauling is familiar. All of his papers are at Oregon State University, most of them. A lot of them are Caltech too, but most are at Oregon State. You look at Linus Pauling's papers, and Linus Pauling's name is very familiar to everyone. You start looking, very closely and paying attention to the co-authors on those papers, and then paying attention to the people who are working in different research groups within the laboratory and how those individuals intersect on different projects. And as well, if in teaching with undergraduates or certainly graduate students, but even undergraduates, if you can get the students themselves to read some of the original papers, to track down the people, for example, who were the co-authors on those papers, to figure out what happened to the people who were co-authors on papers written by a famous scientist or 2 or 3 famous scientists, and to follow their tracks historically. Not only where did they go, but also what did they do, and what were the influences that determined where they did. I mean, again, you wind up one place rather than another, and given your resources there, you may do something entirely different than what you started out. Or you're asked to teach a course in a subject with which you have very little familiarity, and you have to learn it. Or you're lucky enough to have a cafeteria where faculty members or researchers in a big private laboratory go, and you sit around talking with people who are not necessarily in your field. And following another thing for looking at groups is to not only look at the university scientists, but more and more to focus on scientists and the way government scientists do their publications. Take, for example, the U.S. Geological Survey, or take other institutions, say like NASA, and the ways in which the protocols and the rules about the way you can publish, what you can do, as well as funding sources work, and perhaps do some contrast in that vein between the ways in which academic scientists can work and the way in which industrial scientists work and the way in which government scientists work. That'd be a useful way to introduce students. It wouldn't be easy, but you could, as with most teaching, ask the students to do a lot of the work for you on their term papers.
I'm going to take the liberty of making a comment and then asking a question.
Okay.
The comment is you had that wonderful trio with Barry Barish in the middle for the LIGO work and gravitational radiation. And I would say that having him as one of the recipients exemplifies your point of the growth of the importance of collaboration, because it's pretty clear that the whole thing would have fallen apart without Barry Barish's genius at keeping people talking to one another and preventing the siloization that was developing so rampantly. And that's an interesting thing, I think, to consider. So that's my comment. My question is, to what degree, and is it something historians should be interested in, does the existence of the Nobel Prize influence the character of research? The recent book on by the fellow who believed that he had detected polarization in the primordial radiation dust and everything turned out to be, intergalactic dust. He blamed it on his quest for the Nobel Prize, publishing prematurely. And so I'd love to have your comments on that.
I'm not sure I can give a really good answer to that question. I don't doubt that it may have some impact. You're giving an example of someone publishing prematurely. But people, of course, publish prematurely for other reasons than wanting to get a Nobel Prize or try. And after all, the competition between different research groups and different laboratories is very, very old, going back into the late 19th century, but certainly the early 20th century.
He explicitly blamed the Nobel Prize.
Okay. Well, maybe he was justified, but I think he was deluded, perhaps in going after the prize in quite that way. I would just say very quickly that one of the physicists, I wrote a book, which I mentioned, I wrote a book on Patrick Blackett, And he did not get the Nobel Prize for the positron. And the reason he didn't get it is because, I mean, he got it for cosmic ray physics and for nuclear physics in '48. But Carl Anderson got the Nobel Prize for the discovery of the positron. Black actually had tracks earlier, and he was convinced that that's what it was, but he wouldn't call it that a month before Anderson published his paper. So now things are different. I mean, but on the other hand, you know, the Nobel Prize had a lot of prestige in the '30s already. So.
Thank you. So in the history of physics, you sometimes consider issues of metaphysics. You're considering in effect, the history of historians study the history of physics,
right,
which is a kind of meta-history. So in that regard, one of the things that struck me was that in your description of these historians, you were talking about research by individual historians, such as the gentleman you have up on the screen. And I'm wondering if one of the reasons that there's a difficulty in explaining history or physics as it's happening now with these collaborations, because it's not really familiar to the people doing the research. They're more familiar with the idea of the individual academic researcher. After all, the idea of these big collaborations is relatively new in physics too, and that perhaps the story of the individual researcher is just more natural to people who have been studying this field.
Well, I mentioned that I began my own work in the 1960s, and then I also mentioned that the elementary particle physics and nuclear physics were sort of dominating the Nobel Prizes when I was switching back and forth in the 50s and 60s. And certainly people of my generation were very much affected. Of course, it partly has to do too, well, anyway, with what you're studying in textbooks and what you're familiar with. And so there's a time lag there for people who are not in the field. And I'm not in the field of physics, and I was never a professional scientist. I was a historian of science. And so a lot of sort of what comes natural to you is what you learned at a certain stage because you didn't go on. You read it and you talked to people and you visited labs, but it wasn't the same thing as doing physics and physical chemistry and publishing papers in it. And you don't, I mean, again, in any professional discipline, you have a sense of networks. So I have a sense of networks within the history of physics and the history of science. If you're a physicist in a particular field of solid-state physics, you have a sense of the networks. And I gave a different talk a few years ago to a group, and there was a physicist in the audience, and I was talking about co-authorship and collaboration, which has become of more interest to me because I sort of began doing this when I became astonished at what I said to Ingrid about looking at Linus Pauling and then realizing how in my own writing I kept saying Linus Pauling, Linus Pauling, Linus Pauling. And it was not just Linus Pauling. I mean, there's all these people who are backing him up. And he, in any case, then what the physicist said to me, I said, I'm looking at these authorship. I know something, I know, and I've read different journal policies about co-authorship and, first author, last author, alphabetical versus other things, et cetera. And he looked at me like I was crazy, and he said, everybody knows who did the work. I said, okay, all right, everybody knows the work. Now, that's something a historian doesn't necessarily know, right? Because, if we talk to enough people, if we do a lot of oral histories, as say Greg is doing on a project right now, then, you do learn a lot more about, exactly who knows what. But if you're not in the field, it's really hard to catch on just by reading. Yeah, and certainly if you're looking back on it decades later.
Yeah, let me say, too, that there are comparatively few historians who work in teams. And so it's outside of the expectations of many historians that they would look at teams that are subjects as well. That's not true here. We tend to do a lot of team research in the History Center here.
Mary Jo, just a comment to start with. The Cavendish lab in Cambridge between the wars, where more than one or two authors per paper was extremely unusual. Yeah. In fact, had a very social side, both in terms of the Kapitsa Club and the fact that Rutherford insisted on everyone having tea together,
Right.
which was a tradition that continued then in the molecular biology lab at Cambridge. So even though you had one or two author papers, there was a lot of social interaction, I think, behind the work. And I just wanted to ask you about general sort of barriers to entry, you might call it, for readers for history of science. You know, it is no different for physics than it is, I think, for structural biology, that as it becomes more specialized, to actually hook a reader to be interested in something becomes increasingly difficult. And you say it's hard for a writer to write about multiple characters involved in particular research. It's very hard for the reader too, when you have about 17 people.
Yeah. Now that's a very good point. And I mean, it's hard for the writer, it's hard for the reader. The biographical focus, of course, is one that is so successful because we all care about individuals, and we all care about you know, the Bildungsroman, the kind of notion of development and of change. And for a biographer, as you are yourself, I mean, following all the strands in an individual scientist's life is not really so easy. But when you put it together for the reader finds it easy to follow if you've done a good job because you've worked all that out. And particularly for a biographical subject who, whether it's in physics or in some other field, who's touching on many different subdisciplines and has, you know, a very complicated life, the single biographer, because it's usually a single person, as Greg says, it's hard. But then multiply that by trying to get what you would call the human interest into a large biography without turning it into a dictionary, without, you know, turning it into a kind of annotated glossary. It's really quite a challenge, and I think the reader is part of the problem. And in fact, there have been lots of symposia and conferences that have to do with writing biography, and biography remains an extremely popular genre. And someone was asked at a conference at the American Historical Association, why is it that why are there so many biographers? And there's a huge percentage of presidents of the American Historical Association who've written biographies. And someone said, that's where the readers are. You know, certainly for the history of physics, that there is interest among readers in individual, but it's an entree. Biography is an entree into understanding something about the history of physics that's easier than sort of looking at the big picture of multiplicity of authors.
And we have a question back here.
Did you find anything that might indicate that there is a limit to collaboration? Did you find any indication that groups said there were too many people in this group, we couldn't keep track? Or if you get too many people, then somebody isn't doing any work that contributes? Or if you have two people at the same level but divergent views, then they spend too much time fighting? Or, do you understand the question? Is there a limit to collaboration?
Derek Price's infinity of authors. Again, I can't answer that question in terms of, you know, how the teams are. I mean, the comment that was made about Barish and about, you know, his bringing together people is sort of part of that. And I've read several articles that have been written by sociologists about project leaders and laboratory leaders, and again, sort of the notion of credit and how the notion of credit within the group leads to tension and animosity and can sort of break down what the group is hoping to achieve in terms of collaborative authorship. For an earlier period, not the recent period with which I'm sort of concentrating, because I haven't done the history of this very recent period myself. I've just been reading about it. And for example, in my work on Michael Polanyi, who was at the Fritz Haber Institute of what is now the Max Planck Gesellschaft, he was doing research on, he had in his unit two or three different, always he had 2 to 3 at least different projects, maybe more than that going on, and different groups that were working on them, some of whom overlapped on other projects. And he made a particular statement where he said, I can't imagine being able to manage this with more than 10 people. Now, it's very different now in terms of management strategies and all that. That's something, again, that historians of physics could be writing about. But I can't directly answer your question. I think the answer is, in terms of naming a size limit, I certainly can't do it. I mean, it depends on the project, the circumstances, how the whole thing is organized into subgroups. And I would say, too, whether people think that they are getting credit from their immediate superiors and some of their colleagues, and whether they feel that they're accomplishing something in a project that's meaningful.
Another question here.
Can we learn from the history of physics, or are we doomed to repeat our mistakes?
Well, yeah, sure. I think we've got a lot to learn from history in general, and that would include the history of physics. And I think that, looking back at work that's been done in the past, at things that seem like dead ends that turned out not to be dead ends, at looking at projects that seemed not to get recognition at the time and then rediscovered. There's a piece in physics, in the most recent Physics Today, about the advantage of looking at old literature and learning something from articles from the 19th century about work that was done, for example, on Brownian motion, and then how that sort of comes up again in the 20th century. In terms of organization of research teams, I think historians have done a lot of work that's shown that some mistakes were made in organization, apropos of your question, to some extent, and that things could have been more successful if they'd been organized differently. If a research leader, for example, had not been self-absorbed, if a research leader had sort of paid more attention to colleagues than was the case. And of course, some people are simply praised for their collaborative nature, for the way that they were able to organize groups and keep everybody relatively happy. I mean, Dorothy Crowfoot Hodgkin was an example of someone who had intense loyalty from everyone who worked on her for the way in which she was a collaborative person and did give credit and did learn and kept on learning new things herself. And so one can learn from that example. I mean, if you read Georgina Ferry's biography, a biography of Hodgkin, you can learn something from that, I think.
Next question is back here.
So there have been a couple of questions about, how do we rectify the historiography to better reflect the landscape of physics as it historically existed. And some of the answers that we've come up with so far have revolved around, do we do different kinds of studies? Do we do historical studies of collaborations? Do we do them of solid-state physics, of areas that have been under-recognized? And I was wondering if I could press you for a few more thoughts about, how it is that you can develop a different way of looking at the past. And my question is motivated because it's a question that I've been thinking about for a long time. When I arrived in this building 10 years ago as a historian here, I proposed a project wherein we would essentially try and create a better map of the physics community as it existed in the past beyond the handful of figures that we usually have. So we got biographies, basic biographical information of about 850 different physicists to give us something a little bit more representative. And we made a website out of it, and it interconnected them all in a way that kind of brought out some of their institutional networks, at least, if not their intellectual ones. And we did it, and it was very cool, and it still exists if you know where to look for it. But it didn't really do anything, and so I'd love to know, exactly how can we survey the landscape? And
well, let me turn the question back to you. I mean, what was your aim in mounting such a project other than to get the information?
Well, I think the aim was to create kind of a map that people could consult of the community. So it's not something to engage attention so much as it is a resource that you can look to if you want to explore different milieus in the history of physics. So it was a pilot project, and I think it was partially successful, but it didn't, ultimately have a historiographical impact. And so that's my question for you, is how can we create a historiographical impact? Is it simply a matter of, you know, Joe Martin writing a book on the solid state physics and maybe a few more people write a few other books? Or is there a more expansive way that we can go about it? Because I certainly don't have the answers myself.
Well, if you take, for example, the kind of work that's being done at the Max Planck Institute for the History of Science in Berlin, a lot of collaborative work is being done there. I mean, that's been one of the styles, I guess you would say, for the conferences that usually turn into books that have been organized. I mean, at the Max Planck Institute for the History of Science, which of course is dedicated. I mean, it's a group of people with a fundamental faculty, and then other research groups, some permanent research groups, some part-time research groups, and they work as historians on big projects. I mean, one of their projects is big data, and trying to understand data sets and how the data accumulates and how it gets used, and to draw some conclusions from that. And I think that in order to do something that's on the lines of what you're talking about, and that's really looking deeply at collaborative science, I do think it involves collaborative work by historians. And I think, as Greg said, that's not our style. It's not been our style. And I mentioned the Academy of Sciences, and the French Academy of Sciences, and their initial effort to have collective authorship that didn't go anywhere. And I've read some analyses of the ways in which, just precisely in that period, in the 17th century, that the notion of the single literary author really came into being, and the single genius was coming into being, as in contrast to the old notion of craftsmanship and of workshops. And I mean, now if we look back at art, for example, and we talk about Leonardo da Vinci, or we talk about other artists, I mean, how many of us have gone to art museums, for example, and seen attributed to, or from the workshop of, and whether you're talking about painting art or sculptured art or other kinds of art and craftsmanship. That was what the French Academy originally was kind of trying to do, and some of the Italians were. It was this notion of studying the natural world collectively, and then coming up with this sort of consensus in which the individual identities submerged. But everything changed in the 17th and 18th century, and probably no one wants to hear Michel Foucault's name, but he wrote on this, and how the individual author appeared in this period. I have a colleague at my university at Oregon State who talked with me after I'd given a talk that had to do with biography and the writing of biography, and she said, "Mary Jo, it's so strange, because if you look at scientific papers, they're co-authored, everybody works together, and if you look at what we do, it's single authors." And I said, yeah, that's maybe 2 or 3, but it's a very different style. Of course, again, as I was talking about collaborative research, one of the things that I mentioned was the scale of the kind of instrumentation that's used, the kind of work that's being done, can't be done by a single person. And I was talking to one of you earlier about having retired, and that although I don't teach, that in fact I'm still doing research. That's because I need a library. I don't need a laboratory. I mean, this is very, very different. And for historians, I mean, again, we do oral interviews, we go to archives, we do go to these places, but we don't have to have a laboratory. We don't have to have huge, huge grants in order to do our work. Sometimes we get them. Sometimes we, some of us who are really, entrepreneurial can have big grants and lots of graduate students working with us, but most of us don't.
One last question.
When you talk about how many people is an optimum number of people for a team, that's such a very arbitrary thing, because in many physics problems I was engaged in with a team, You built the team of experts in many different facets so they could all do their part of the journey and the study we had to do. And one didn't usually pick two who had exactly the same experience and did the same thing, because that would just be overburdening, or not overburdening, but overstaffing what was needed. And it's so interesting. Just look at the spectrum of people you need to form a team. You have some nice people, and you have some outrageous, arrogant people, and you have to get them to work together, so you need a good leader. I had a professor named Louis Alvarez, University of California, and he was the most fun and the nicest man in class, but if you went to him during his office hours, he'd beat you into a pulp. And one of his favorite stories was about a professor, Rowland, at Johns Hopkins. And Rowland was called to be an expert witness when they were trying to decide what sort of power they would have in New York, AC or DC. And so one of the examiners started to try to annoy Rowland. So he said, "Tell me, Professor Rowland, who do you think is the most brilliant physicist in the world today?" And Rowland said, "I am." And after the hearing, one of his colleagues said, "How could you say a thing like that?" And Rowland said, "I was under oath."
I'll remember that one.
Okay, well, that's a good note to end on. So thank you very much, Mary Jo.
Thank you
Wonderful
all.
talk. Thank you for the questions from the audience, and thank you for the questions and comments online. I've realized that this multiplies the things that I need to pay attention to having live streaming going on. So I need to follow my email and Twitter and Facebook, because different comments came in from all three different places. So we'll work out the bugs on this as we go along. Thanks very much, and I hope to see many of you back again on October 3rd, just about 3 weeks away from now. Thank you.